Hello and welcome back to Calculus 2, the section 8.3 on trigonometric integrals. So lock the doors. No one leaves until we're done. So it works, great. Few things that you must know before we get to calculus. These are the formulas from pre-calc that you absolutely must know. Number one, you must know, let's just put u sub here, that's a given. You must know all 6 derivatives and integrals for trig. You must know the reduction formulas. Actually, I should be writing this out. There you go. So u sub, and now we have to have the derivative of sine x is cosine x. The derivative of cosine x is negative sine x. The derivative of tangent x is secant square x, thank you. And the derivative of cotangent x, please help me, is? Thank you, minus the cosine. The derivative of secant x is? Very good. And the derivative of, oh, trust me, you're going to know this without any cheat sheets tomorrow. And then we have the cosecant x is negative cosecant x cotangent x. You read integrals backwards. Integral of cosine is sine, integral of secant squared is tangent x, integral, right, plus c on each one of them. This is pattern. You must know all of them, but look at the pattern. The trigonometric pairing is sine with cosine, tangent with secant, and cotangent with cosecant. So these are the trigonometric pairs. They do not venture out of this pairing. Now, what happens if you have tangent cosecant pair? Tangent cosecant pair. You immediately know that none of your integration calculus will work out. That's immediately triggering that you are supposed to convert everything to sines and cosines. Okay? So when you get something that is not paired this way, that is immediate trigger that you have to go to sines and cosines basics. You know what the tangent is, sine over cosine. You know that cosecant is 1 over sine, right? So you have to use all of those formulas to convert these things. If you are not in them. Now, if you are in the pairs, then you use other formulas. So you must know this. The next part is power reducing formula. So sine squared x is equal to 1. Anyone help me?
Plus
1
minus cosine
2x over 2. And the cosine squared x is? 1 plus cosine 2x over 2. Yes, 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 yes. And finally, we have those 9 Pythagorean identities, which we can just write 3. So sine squared x plus cosine squared x is?
1.
Thank you. And then 1 plus tangent squared x is squared x. And then 1 plus cotangent squared x is? Thank you. Do you see that this pairing is following the pairing for the derivatives and integrals? So we're still good, right? We see that the pairing? So from here, right, we have. What else can you add to this list? You can add, these will be used actually later in Trig sub, the double angle formulas. So sine 2x is 2 sine x cosine x, so that's a good one. And the cosine 2x is cosine squared x minus sine squared x. Bueno? There you go. This is it. Now I understand if you never had a trig course, this sounds like, well, it's like 10% of the formulas that you get in the class anyway, so it's okay. You must know U sub. You must know now which way the derivative works, right? The derivative, you read it backwards, right? The integral of this is sine x. So you just read these from right to left. We are ready to do some calculus, maybe.
Can you go back down yet right there? Hold on.
I know. "27 notifications. Yeah, 27 messages across the platforms. Blocked. Blocked for adding to it right now. All right, you all done writing? Let's go and see. Just everything can wait except the one where I get to trigger someone for a comment. I love that. Anyway, so the first problem is the problem from Calculus 1. So this is a Calc 1 problem where you have sine to the 8x cosine x dx. This is clearly a trigonometric integral because it contains trigonometric functions, which you solve using what? Use U sub, right? So what's U? Sine x. What's du? Dx. So now we substitute. It becomes u to the 8 du. See, this whole piece over here is du. Do we all see that? And now this is u to the 9 over 9 plus c. And then we use the sentence, I don't care about u, I care about the x, for 1 over 9 sine to the 9x plus c. Is this problem possible to do the other way, where my u is cosine x? And the answer is no, right? Why? Well, if you make, remember what I said last time, if you make a wrong substitution, you're just going to make the problem worse, right? You will see it. So if you try to go u equals cosine x, and then du equals negative sine x dx, and you try to plug this in on sine 8x cosine x dx, you see that you need one sine combined with dx. So you have to peel it off, and you will get sine to the 7x. Cosine x becomes u, and then the one sine x you peeled off, dx becomes du, so your integral is now sine 7x u du, and there is a negative in front. Do you see how this is worse now? Right? Because you don't have anything to deal with this sine to the 7th. So when you make a wrong substitution, you will know, because hell breaks loose immediately. There's nothing that we can do with this thing here. If you do it right way, right, it all works out, sometimes sooner, sometimes later, but yeah. So that's that. So what are we going to do now? Well, the next problem is the problem that you have to have seared in your brain, because this problem is going to be the part of other problems. And that problem is integral of, let's say, cosine squared x dx. You need to be able to do this in your sleep. So what do we have there? We have the formula. The formula I listed here. It is the only way to solve this problem up until we reach chapter 10. Then you'll have more options. But now, this is it. 1 plus cosine 2x over 2 dx. You kick 1/2 outside, and now you have the integral of dx plus the integral of cosine 2x dx. You give a half to each by using these parentheses. So this is 1/2. The first integral is just x. The integral of cosine is sine. So we have plus 1/2 sine 2x, and then everything plus c. And you're done. So this one and the sine one are a must, because they will be parts of a bigger problem. It's coming up, so you'll see it. That's the integral of 1 dx. I didn't write the 1, but...
Okay, so where does that, is that 1? What's that 1? Oh.
Because this half is out, right? The half is out. So when you remove this half, what's left? Two integrals. This integral and this integral. When you kick half out.
I see.
Do you know where the half came from in front of the sine 2x in the answer?
Oh, it came from this. Whatever that number is, it's gonna be this number. Because when you're, oh, that's actually worth mentioning, guys. The integral of, let's say, let's use sine ax dx is going to be negative 1 over a cosine ax plus c. And I'm just going to point to these a's. So now when you have an integral of secant ax tangent AX. So secant 3x, tangent 3x, integral of that would be secant 3x over 3. So you always have this 1 over a in front when you're integrating if this is not x. It comes from basic u sub, because you use this as u, and right, so we're just skipping those steps because we memorized a for ease and memorized a for trig in derivatives. Now we're doing the same thing for integrals. All right. So this is
So it's really negative?
integral of sine is negative cosine. Derivative of sine is positive cosine.
No. He's just showing you, like.
Calc 1 so far.
Yeah, to do something, I think you have to do it yourself.
So we are done with the review. All right. What have you seen so far has been reviewed, whether it's pre-calculus or calculus 1. Let's start calculus 2. Welcome. Integral of sine to the m x cosine to the n x dx, where m and n are integers. So now we are going to have certain patterns that you have to pick up and use. The first problem is going to be sine to the 6x cosine cubed x dx. And I'll write over here in blood, one of the exponents is odd. That is very important. You are going to get a flavor of the problem that has one odd exponent, or you're going to get a problem with two even ones. That's the one you don't want, right, by the way. So, for sines and cosines, there are two flavors of problems. One flavor has an odd exponent. The other one can be anything. So this 6 could be even and odd, doesn't matter. So a problem with when one of these two is odd, that's a flavor. And then the second flavor is both even. Now let's deal with this first, and then we'll deal with both even. So flavor, where you have one odd exponent, is you go to whatever is odd and you peel that one off. So I'm going to immediately peel one cosine off because I need to save that cosine for dx. So whatever is odd, you are peeling off that one function and you keeping it in a bank for dx. So I am starting with sine to the 6x cosine squared x cosine x dx. So peel off your negative, right? So your odd exponent. If sine was odd, or if both are odd, you pick one. Doesn't matter, right? If the both are odd, you pick one, which one you want to peel. If you only have one odd, you have to peel that one. Now, you put this in a bank for dx. Now, if cosine is going to be your dx, that means that sine is your u. I mean, cosine x dx is du. Then that means that your u has to be sine. I still have this. What do? Yes! We transform all of these into sines using the formula that transforms them into sines, which is why you have to know these. These three formulas you're going to use in every single problem. You see these three? Every single problem is going to use them. So, did I say at the beginning of the class, lock the doors, right?
Yeah.
Exactly. So now, this becomes sine to the 6x, and this becomes 1 minus sine squared x, and we still have our cosine x dx in the bank for du later. Let's do some algebra. This is sine 6x minus sine 8x times cosine x dx. And finally, we can use u sub, right? Right. U is equal to sine x, du equals cosine x dx. So the entire problem transforms into u to the 6 minus u to the 8 du. U to the 7 over 7 minus u to the 9 over 9 plus c, which is 1 over 7 sine 7x minus 1 over 9 sine 9x plus c. Awesome. So for this entire problem, where's the money? Money is right here. That's where the money is. When you peel off the odd exponent, the remaining exponents are odd. And if you have odd exponents, you can break them into squares and transform each one of those using this formula. That's what did I say? Yeah, sorry. When you peel one from the odd, you get even, and then you can use this. This is the flavor when one of the two exponents is odd, or if both are odd, you can still use this method. You can just pick whatever one you want to peel. Flavor number 2, both odd. Integral sine 4x cosine squared x dx. What did I say? Oh my. Yeah, I am. Yeah. Okay, we're done. So flavor when both are even. Will our method of peeling one to keep it in a bank work? And the answer is clearly not. Because if I peel, I'm going to erase this. If I peel one of the cosines to keep it in a bank, to do the u sub like in a previous problem, I am stuck with this cosine that doesn't have a square on it to be transformed back into the, right? So I am doomed. That's 7 O's, right? That method won't work. So what should I do now?
Turn the sine to 4x into 2 sine to 2x's and then convert those.
How about we convert the cosine? Convert the cosine using 1 minus sine, and then we're going to have sines across the board. Now that still means that you can't use u sub. But what can you use? You can use the force. You can use power reducing formulas. Now let me make that much worse. Nested power reducing formulas. Yes, because your fourth, right, is square square. So that's nested power reducing. Multiplied by the cosine squared over there, right? So before we start this problem, let's go, everyone, right? Warm it up, warm it up, warm it up, warm it up. Do the fingers. You can do this. Stretches your tendons, like that. And this as well. These are good stretches before the problem that's going to take 30 minutes. Yes?
It's like the engineering application for
Calculating energy for oscillations. There is mechanical and electrical. So you are going to, I mean, most of this is mathematical gymnastics because E is missing in this, but you can always add E to the fire and have it. So yeah. Of course. Sine 4x, 1 minus sine squared x dx, which is sine squared x squared, 1 minus sine squared x dx, and then power reducing 1 minus cosine 2x over 2 squared times 1 minus cosine 2x over 2 dx. That's just a standard power reducing formulas, nothing right too special. Now we have to do it again, right? Because you have that square that you have to apply there. How about we kick a quarter outside because we can? 1 minus 2 cosine 2x plus cosine squared 2x. That's the first one. And for the second one, I can come up with the common denominator, right, of 2. Which would be 2 minus 1 plus cosine 2x, and then I have dx. Yeah, I know, it's algebra. Now I'm going to take this 2 and multiply outside into 1 over 8. And I have 1 minus 2 cosine 2x plus, hey, it's cosine squared. Power reducing formula again. So 1 plus cosine, and this time is 4x divided by 2 because your input is 2x and the formula doubles it. So 2 times 2 is 4x on this new line. Times, now we already kicked this half outside because quarter times that half is 1 over 8. So all I have over here is 1 plus cosine 2x. I don't get to do anything with that. Now we know that there is no product rule for integrals. We have to FOIL this, which will bring in extra squares, and it will bring extra power reducing. At this point, maybe you want to turn the notebook sideways to fit everything in one line because you don't get to generate paper like I do. Right? So now we have a 1 over 8 integral, and now we have some foiling to do. Are we ready? 1 times this mess is 1 plus cosine 2x. That was me multiplying 1 into both. We are doing basic algebra. The next step is to multiply this into both. And then finally that fraction into both. So now negative 2x, negative 2 cosine 2x, I picked the worst possible problem I could. Minus, and now I have 2 cosine 2x in there. When I multiply cosine 2x times cosine 2x is cosine squared, right?
Oh yeah, you said cosine 2, so
Cosine squared 2x.
cosine squared 2.
2x. Maybe if I write it, it would be better. So now I'm done with one, I'm done with this one. So that's 2 out of 4, because now I have to multiply everything by a half. That's a good effort. So we have plus 1/2 and plus 1/2 cosine 2x. That's when I multiply this one into both. And finally, the most dreaded term of this problem, this times both. So plus cosine 4x over 2. Is that someone passing out? I heard the sounds. And then we have plus 1/2 cosine 4x cosine 2x dx. The first parenthesis has 4 terms. The second parenthesis has 2 terms. When you multiply them, 4 times 2 is 8 terms. So we had to have 8 terms, right? Now you collect like terms to reduce this integral. I have a 1 and a half. Oh no, not that half. Half is right here. So that's 3 halves. So that collapses into 3 halves over here. What else do I have? I have a cosine 2x. So let me underline them red maybe. I have a cosine 2x here, cosine 2x here, cosine 2x here. So I have 3 of these. So cosine, and you can say apple minus 2 apples plus half of the apple, right? Or strawberry, I don't know, whatever you're not allergic to. So 1 minus 2 is negative 1, plus 1/2 is negative 1/2. Negative 1/2 cosine 2x. So that's that. The next term is cosine squared 2x, and it's the only one of the kind, so we just get to copy that one.
Real quick, you did 1 plus a half plus a half, you got 3 halves?
You mean for the first one? Yeah. No, I just have 2 of them. 1 and 1/2.
Oh, no.
This half is attached and this half is attached, so no. Here I have to combine this, and they combine into a negative half. So the next term is this solo term, which is this one. So that's negative 2 cosine squared 2x. Yeah, that one actually has to be power reduced. Plus another solo term right here. No other 4x's around. This one is different, right? Because it's attached. So copy that one. Cosine 4x over 2. And now plus $1 million term. This is why immediately when I saw this, I said, yeah, this is the worst possible problem we could have. But I mean, what can you do? You can do sine squared, cosine squared, that it's easier than this. If you go if you do fourth and a fourth, you're just going to make it worse than fourth and a square, right? And you have to do even and even to come up with this stuff. So the only cheaper problem that you can get than this is sine square, cosine square, right? Okay, ready? Just want to try to get this ready for you. Your phones are ready, I hope. The next term is the last term here, consists of different angles, right? If this x is 30 degrees, then this is 120 and this is 60. So they're always different angles because this one is times 4 and this one is times 2. So no matter which x you pick, they don't get to be the same number. What do? You can't use u sub because they are not the same. So the only thing available to you is this. Now, no one knows these formulas because these formulas, you were given these formulas when you took your trig class, right? You took your trig exam and the product to sum formulas were given to you. He's taking a picture. All right, now. Road Rock sign. Road Rock Club gangster, right? So what do I have? I have cosine A times cosine B. Your A is 4x, your B is 2x. Here is your cosine 4x, cosine 2x. Here is your 4x, 2x, 4x, 2x. I can see the headache coming up. Oh, by the way, welcome to Calculus 2. I'm not sure if I ever mentioned that since the beginning of the course, but now we have unleashed the beast.
The half that you already wrote down, is that in addition to this?
No, one more half. One more half. There is a half from the problem, and you're doing one more half. I just want to write this down. So this is going to be cosine of 6x plus cosine of 2x. And then close the dx. So I am using this formula. Where can you can land anywhere here with these double, right? So that's what I said. When you see these problems, what you're doing is you are hoping that one exponent or both are odd. And then you get the previous problem. You peel the odd, everything is cool. You have two evil ones, right? Two even ones, right? Look, it's like, I'm done.
We're all done.
What would those be called if I were to Google them?
Product to sum formulas. They are also featured on the cover of your textbook. Product to sum formulas. So when you do the even, those formulas might, not will, might kick in. Okay, so.
So do we need to memorize this product to sum formulas then?
No.
So you will give us those for the test.
No, I'm just not going to put this.
Then why are we learning? Oh my god. No comment.
This was a direct request for this to be on a test. This is the way I interpret things.
No.
So now, thanks to Angel, I have to provide the formulas when I ask this.
I said 10 times.
I'm just wondering why we're
divided by
learning
five.
if we're not going to get paid.
That was my request.
So 3/2 minus 1/2. First of all, this is an excellent conversation starter for a Thanksgiving dinner, for instance. You work this out.
I'm your family.
I'm serious.
My family would be like, get out of here. Let me get another drink.
Exactly.
Note that I use the formula, the power-reducing formula. Power-reducing formula is over 2, which killed the 2 in front. So there is no over 2. Are we all bueno?
Happened here?
There's something different happening.
He wrote that in. He wrote that in while we were on the.
Oh yeah, I wrote this in while it was a different screen.
Yeah.
If you watch the video, it will be continuous. Plus 1/4 cosine 6x plus 1/4 cosine 2x dx. Okay, now we're talking. No more exponents. It's wonderful. I have -1 over here. So now these 3 halves become 1/2. I have a negative 1/2 cosine 2x and positive 1/4. So that's going to be negative 1/4 cosine 2x. I have a negative cosine 4x and a positive 1/2. So that's going to be negative 1/2 cosine 4x. And finally, plus 1/4 cosine 6x dx. No, we're not done yet, so it's good, right? You're right on time. And here's our basic Calc1 integral finally. 4 integrals. Given that I didn't make any mistakes, right? We could kick a half out to make this a little bit easier. So now that's 1/16. Integral of 1 minus 1/2 cosine 2x minus cosine 4x plus 1/2 cosine 6x dx. And 1/16. Integral of 1 is x. Minus the 2 jumps out, so it's going to be 1/4. Integral of cosine is sine 2x. 1/4 jumps out. Integral of cosine is sine 4x. Plus 1/6 comes out, so it's 1/12 sine 6x. And don't forget plus c, right? That's like when you put the cherry on top, like bing. And there you have it. Easy peasy. 2 pages, right?
We've got 2 problems.
Yeah. Oh wait, the secant and tangents are coming. This is a warm-up.
When are you going to teach me to do square root tangent?
We are done with sines and cosines. These are the 2 flavors you have. Flavor number 1, one or both exponents are odd. One or both exponents are odd, in which case you peel off the odd sine or cosine and you keep it in a bank for du, and then you transform the rest to the other function and you just run basic u sub. So that is the easy, but the other one is easy too, it's just annoying with algebra. The second one is both even, and that is where we get to do some algebra, because you get to convert these and then you get to keep hitting them with the power reducing.
Would you ever have 2 odds?
I'm sorry?
Would you have 2 odds?
Yeah, 2 odds are also, 2 odds are here. 1 or 2 odds.
Okay, so would you?
You will just Pick either one and peel off. It doesn't matter. You will be able to. I believe your lab has a two-odd question where part A says peel sine, part B says peel cosine. So your lab should have a question that is forcing you to do this, and you have to get the same answer at the end. So lab should have that question. It's a very good question, right? Because you should be able to arrive the same answer using peeling either sine or peeling the cosine, because you have two odds, right? Now the two evens is like next time anyone complains that their problem is too long, you say, but look at this. Secant tangent pair. Whatever you learn for secant tangent works exactly the same way for cosecant cotangent. We do not have to learn cosecant cotangent pair for these trig integrals separately or at all. You just have the formulas look the same. You're just having minus signs floating around to annoy you. That's that. Now, I start this with writing the integral formulas. Integral of secant squared x dx is tangent x plus c, and integral of secant x tangent x dx is secant x plus c. These are the formulas from your Calculus 1 that will be used to solve the problems. So now what? Right? What kind of questions we have here? Well, we don't have the cases. We are focusing on what do you get to keep in the bank for your du as you are working on the u sub. So for that, you need to be the master of the derivatives, right? The derivative of secant x is secant x tangent x, and the derivative of tangent x is secant squared x. Which means, when you write it this way, switch to, I guess, orange. These guys here would be your u, and these guys here would be your du. So what do you get to keep in a bank on a side for your du? You get to keep either secant tangent or secant squared. So now, let's do an example. Tangent cubed x dx. That's a problem. All right. It's not a basic integral. It's not a u sub integral, right? I can't do any of that stuff until I do some mathematical witchcraft here. I start by peeling off two tangents. So I have tangent x times tangent squared x dx. Now, why would I peel tangent squared? Tangent squared is going to be converted into secant squared using the Pythagorean formula. So, further, this is tangent x times, and the Pythagorean formula is 1 minus secant squared x, and then you have dx. Now I have to scroll all the way to the top of the lecture to point out the formula which we are using. Now, since I am transforming tangent into secant, oh, it was supposed to be secant minus 1.
Yeah.
Yeah, secant minus 1, sorry. So I'm transforming tangents into secants. I have to flip this and move one to the other side. So this, I have it wrong, so we'll fix that. It should be secant minus 1. So secant squared x minus 1. Now what do we do? We have integral of tangent x secant squared x minus tangent x dx, which breaks into two integrals because you have a minus, right? So there is the integral of tangent x secant squared x dx minus the integral of tangent x dx. Yay! For the first integral, I can use u sub because derivative of tangent is secant squared. So we are keeping that in a bank for du. So I have u equals tangent x, du equals secant squared x dx. So the first half of the problem is simply integral u du. Minus, now the second integral here is integral of sine x over cosine x dx, because the way to integrate tangent, right? Tangent is not a basic function for integration. You have to change whenever you have a single tangent. We did this last. Did we do this last class? No, I did this last night with my Calc1. When you want to integrate tangent or differentiate tangent, right, you can write it as a sine over cosine. So now you still use u sub. We do the orange. Since we already used u for tangent, how about the g sub? So g is cosine x, and dg is negative sine x dx. So now the plus, right, the minus from here and the minus from there, and we get integral of dg over g. This is going to work to be gg at the end. So now we have u squared over 2 plus ln of g plus c, which is 1/2 tangent squared x plus ln absolute cosine x and plus c. Ta-da! So satisfying when you get to put this box at the end, right? If you are bothered by the fact that there is a cosine in your answer, because you know that tangent and secant are pairs, you are welcome to steal a minus sign from here and make this into 1 over cosine, which would be secant, and it will be just minus ln secant. Whatever makes you happy, right? This is a math class. Your happiness is our primary concern. Right. Yes?
So you just did like you did a u sub, and then you did like g as your other variable for like a different...
For the u sub again.
Thing. Yeah.
So I did 2 u subs here, which is why I stated at the beginning of the class, the first line was, if you don't know u sub, right. So these are 2 separate u subs, but I used g because u was tangent for this half of the problem. So I can't use u is tangent for the other half because I'm dealing with sine and cosine.
And you can do this as many times as you want with any
Yes.
problem, technically.
So, and you can pick any variable. I could have picked v, so use u and v, but I didn't because then we interfere with integration by parts and write product rule, and So I just pick G because G is not used for anything in terms of substitution. Pick S, pick whatever. S is another one. So U sub for this one because we had components for U sub, and U sub for this one because we have components for U sub. Now, obviously, you practicing these problems and especially struggling with the lab will pave the way in which, right, you're going to move to come up with these things.
So what sections are in lab one, like the first, you said there's 2 labs for chapter 8.
So the first lab covers first 4 or 5 sections, and then the second lab covers the rest. And this chapter, so in the new, the chapter on differential equations is new. It used to be a single lecture, 7.9, on differential equations, just to give you the preview of what's coming up in the course, right, of differential equations. You don't see even the 0.1% in that lesson, but that's okay, right? What they did is they created a chapter with 4 sections, where they took the pieces of this one lecture and expanded on each one of those. We're not going to do the entire chapter. We're going to cherry pick a little bit, just so it's going to be technically mushed in the one section with the highlights, definition and so on, right? So, and that should be on your second part. There's much more interesting things coming up in this section when we are done with the first half. So, chapters 8 and 9, and that's your next exam. Chapters.
I mean the whole course. We're up to 12.
Yeah. The one that says parametric equations and polar.
Did you send out the syllabus?
I have to.
Even though I gave you a piece of paper?
What piece of paper? Oh yeah, you did. I probably left it with the exams in the office. We're gonna get to see it later. But on the bright side, how about another problem? Raritan, 1 hour. All right, so basically with these problems, you are just trying to do whatever you can to fit the U substitution for secant tangent pair, which is the same for cosecant cotangent pair. So let's just pick random problems from and practice. How about, no, integral of, well, 10, I'm going to kick it outside, 10 tangent to the 9 x secant squared x dx. What's the derivative of tangent? Secant squared. So is this a one-step problem? Yes. This is Calculus 1 problem from 5.5. Because everything is set up. You have the bank that contains secant squared, which is the derivative of tangent. So your u is tangent x. Your du is secant squared x dx. So your entire problem is 10 integral u to the 9 du equals to, what does this mean? Just do it. Very good. All right, next problem. It's a test-worthy problem. Now, little modification on this. If I am to have the previous problem, talking about the test-worthy problem, how about if I just spice it up a tag? What have I done? I took the secant squared and made it a secant to the fourth. What happens now?
All hell breaks loose.
No, not actually in this one.
Oh, okay.
This is a test-worthy question, right?
Can't you just
Power reducing?
Nope.
Power reducing.
No power reducing. Only sines and cosines.
Do you peel off secant squared x?
Yes! Peel off secant square. You have a secant square and a secant square. One secant square stays in a bank. What happens with the other secant square?
It becomes a DS.
B becomes tangent.
It's close.
Yeah, all of the letters were off, but yeah. So tangent to the 9x, and now you have a secant squared x and a secant squared x dx. So here is the bank for dx, du. This secant needs to become 1 plus tangent squared x. So we have 10 integral tangent 9x times 1 plus tangent squared x times secant squared x dx. Cool. And then we multiply, just basic algebra now. That's tangent to the 9x plus tangent to 11x secant squared x dx, which is the bank. U sub, u is tangent x, du is secant squared x dx. The whole problem becomes 10 integral u to the 9 plus u to the 11 du. And now you integrate. That's 10 u to the 10 over 10 plus u to the 12 over 12 plus c. Put the tangents in.
how did it become tangent to the 11?
It becomes 10.
When you multiply, 9 plus 2 is 11, right?
The 10 up.
Oh no, he doesn't take that straight to the down.
So the final over here, you can take a half out, kill this 10 into a 5. And you have 1/5 tangent to the 10x plus 1/6 tangent to the 12x plus c. Maybe I should distribute, you're right, because then it kills this, it kills the fraction, becomes a 5 over 6 over here. Okay, yeah, you're right. For the third time today, I'm gonna agree with you. Awesome. We are good. One more problem and then we're going to do something else after the break. Just one more.
Usually I don't worry about it before
I just have to do some practice because all that great stuff is slightly faded in my head.
Can we do a definite integral?
No, it's not a problem.
Yeah, that's what I'm looking for.
Like that, like yeah, there you go. Whatever.
But
No.
if it's integration that's hard, I wonder if you can do it. The limit you solve is the integration by fraction of the case. And we'll do the true problem. Well, it's not that hard if it's a definite, because all you're doing is plugging in the x. Top minus the y.
You know the one for the ball.
We're gonna have like 5 questions on the exam, right? It's gonna take us 2 hours to do, or actually 25, 30 minutes to do one question.
I can't be afraid.
That's because I'm going slow. You are much faster.
You can't be afraid, you just gotta go for it. They'll give us more time again, right?
And he's gonna modify, because he saw what happened last time.
I don't think he cares.
No, he'll modify it.
Either way, he
just
gets
said-
paid.
He said that everything is beforehand, you know,
How about some integral of cotangent cube x or theta, cotangent cube theta d theta from pi over 6 to pi over 3 to make you guys happy because it's a definite integral and it's just one cotangent thing.
Are we gonna have something like this on the test? Like with definite integrals?
Yeah, why not? You just compute the elements, right?
Remember, the theta is just an x. It's just
Yes.
Why did everybody have to bring this up?
Well, because this is on
Oh, I'm gonna put it on anyway.
definite integrals on the lab, so we got it.
It was,
Plus, it's on homework and it's an exam. I mean, I don't have. Okay, how about we end now?
No, we got it.
Oh, okay. Cotangent cubed. Great. What are my 2 banks for cosecant cotangent? One of the banks, 2 banks, right? The derivatives. So you have the derivative of cotangent x is very good. And then you have the derivative of cosecant x is excellent. I gave you enough time. It has to be instantaneous. So the 2 banks that I need for my derivatives are either secant cosecant squared or cosecant cotangent. Those are the 2 banks. Now, I hope you see that if I break the cotangent theta into cotangent times cotangent squared, we can use the Pythagorean theorem to create cosecant squared, and then we would have the bank for our du. So integral pi over 6 to pi over 3 cotangent theta, and now cotangent squared is cosecant minus 1. Cosecant squared. Theta minus 1. The theta, distribute. Cotangent theta, cosecant squared theta minus cotangent theta d theta. We have two integrals again, two different substitutions again. I have u equals cotangent.
Why did you change?
Make it a negative something and a negative.
Flip the limits.
What do you mean?
No, always pi over 6 on the bottom. Pi over 6 is smaller than pi over 3. Always pi over 6 on the bottom. And my du is negative cosecant squared theta d theta. And on the other side is puppy over here, is cosine theta over sine theta. So I have the u substitution, not u substitution, g substitution. G is sine theta, and dg is cosine theta d theta. Integral cotangent is u du, and there is a negative that we have to worry about, and then the minus. On the other side I have integral of dg over g, dg over g, and we have to figure out limits. The second one is easy because sine of pi over 6 is 1/2, and the sine of pi over 3 is root 3 over 2. So those limits are easy. Now, what is the cotangent of pi over 6? Cotangent of pi over 6. Well, that's going to be cosine of pi over 6 divided by sine of pi over 6. Cosine of pi over 6 is, very good, divided by the sine of pi over 6. So my limits are, the bottom is root 3, and when I plug in pi over 3, cosine of pi over 3 is 1/2, and the sine of pi over 3 is root 3 over 2. So the upper limit is root 3 over 3. Then you go, oh, the bigger number is on the bottom. Oh, we can switch that and kill the minus. So when you integrate this, it's going to be u squared over 2, computed from root 3 over 3 on the bottom and root 3 on the top, because I killed this negative. I switch the limits. Minus ln of g, computed from 1/2 to root 3 over 2. 1/2 upper limit, so that's root 3 squared minus root 3 over 3 squared minus ln of root 3 over 2. Minus and minus gives us a plus. ln 1/2. No plus c now. So this is 1/2 of 3 minus 1/3 minus ln root 3, minus and minus is plus ln 2, plus ln 1 minus ln 2. So these two cancel. This one goes to 0. And that's 9, 8, 4/3 minus ln root 3. I hope. Something along those lines. Straightforward.
Yeah.
So, what you can do now with the video is you can play it on slow motion, right?
That's what we were just saying.
Where did you change the sign? Where did you, oh, the negative in the front.
Yes, negative in the front. You change my limits.
Okay.
Yep, negative in the front. Calc 1 5.4. Working with integrals, right? All right, great. So there are your trig integrals. You will probably spend considerable time working and practicing these, but let's see next section after the break, because next section is called trigonometric substitution. You are taking integrals that have x's and square roots and so on, and you're turning them deliberately into the trig integrals so that you can use this to solve them. That's trigonometric substitution. So the best of two worlds, right? You have the u sub plus the trigonometric integration, and then you will have to go back and unwrap that using inverse trig. That's the next one. So after the break, we'll see a few examples of that. Bye.